The impact of a natural or man-made disaster is usually compounded by the inadequacy of temporary soft-skin shelters. Some of these in parts of Afghanistan, for example, are destroyed in as little as 3 weeks by the harsh conditions. Although it can take weeks for people to die of starvation, hypothermia can kill overnight. As medical relief teams know, keeping a tented field hospital aseptic is almost impossible. So infections increase the scale of the disaster. Recent disasters, such as the Haitian earthquake, have demonstrated the desperate need for key infrastructure from day one of a crisis. Concrete canvas shelters are an award-winning technology that has been described as buildings in a bag. A concrete canvas shelter can be deployed by only 2 people in under 1 hour. The core technology is a revolutionary new material called concrete cloth, a cement-impregnated fabric. Concrete canvas shelters consist of concrete cloth prefabricated onto an inflatable plastic inner with steel security doors at both ends. The shelters are deployed in 4 simple steps. Step 1 is delivery. The shelter is delivered folded and sealed in an airtight sack. Step 2 is inflation. The shelter is inflated using the electric fan provided. Once inflated, it is pegged down around the base and is now ready for Step 3. Step 3 is hydration. Water is sprayed onto the shelter until the surface is saturated. Any water can be used, even seawater. The final step is setting. The concrete cloth cures in the shape of the inflated inner, and 24 hours later, the concrete canvas shelter is ready for use. The shelters are modular and can be docked together, expanding the space to meet operational needs. The shelters can be covered in earth, sand, or snow, providing an excellent thermal performance. The hard, fireproof shell provides a level of security not possible with soft-skin structures, protecting stores, equipment, and personnel. Concrete cloth is a ceramic and will not burn. And the sealed plastic inner enables a sterile environment, vastly increasing frontline medical capability. The highly efficient shell structure uses a fraction of the material of conventional buildings, reducing the carbon footprint and impact on the environment. Concrete canvas shelters. In less than a day, up to 54 square meters of hardened, sterilizable space that has the potential to last over 25 years. For further information, visit concretecanvas.co.uk.
how to get there. So, first of all, to get a kilogram, for example, to a moon surface, it will cost about $200,000. Very expensive. So you want to keep it very light. Second, space. Space is limited. All right, this is an Ariane 5 rocket. The space you have there is about 4.5 meters by 7 meters. Not that much. So it needs to be an architectural system that is both compact or compactable and light. And I think I've got one right here. It's very compact and it's very light. And actually, this is one I made earlier. Now, there's one problem with it, that inflatables are quite fragile. They need to be protected. Specifically when you go to a very harsh environment like the moon. Look at it like this. The temperature difference on a moon base could be anything up to 200 degrees. You could have on one side of the base, it could be 100 degrees Celsius. And on the other side, it could be minus 100 degrees. We need to protect ourselves from that. The moon also does not have any magnetic fields, which means that any radiation, solar radiation, cosmic radiation, will hit the surface. We need to protect ourselves from that as well, protect the astronauts from that. And then third, but definitely not last, the moon does not have any atmosphere, which means any meteorites coming into it will not get burned up and they hit the surface. That's why the moon is full of craters. Again, we need to protect the astronauts from that. So what kind of structure do we need? Well, the best thing is really a cave, because a cave has a lot of mass, and we need mass. We need the mass to protect ourselves from the temperatures, from the radiation, and from the meteorites. So this is how we solved it. We have indeed the blue part, as you can see, that's an inflatable for a moon base. It gives a lot of living space and a lot of lab space. And attached to it, you have a cylinder, and that has all the support structures in. All the life support, and also the airlock. And on top of that, we have a structure, that dome structure, that protects ourselves. Has a lot of mass in it. Where are we going to get this material from? Are we going to bring concrete and cement from Earth to the moon? Well, of course not, because it's way too heavy. It's too expensive. So we're going to go and use local materials. Now, local materials is something we do on Earth as well. Wherever we build, whatever country we build, we always look at what are the local materials here. Problem with the moon is, what are the local materials? Well, there's not that many. Well, actually, we have one. It's moon dust. Or, fancier scientific name, regolith. Moon regolith. Great thing is, it's everywhere, right? The surface is covered with it. It's about 20 centimeters up to a few meters everywhere. But how are we going to build with it? Well, we're going to use a 3D printer. Whenever I ask any of you what are 3D printers, you probably are thinking, well, probably something about this size, and it will print things that are about this size. So of course I'm not going to bring a massive 3D printer to the moon to print my moon base. I'm going to use a much smaller device, something like this one here. So this is a small device, a small robot rover that has a little scoop, and it brings the regolith to the dome, and then it lays down a thin layer of regolith. And then you will have the robot that will solidify it layer by layer until it creates, after a few months, the full base. You might have noticed that there are quite a particular structure that we're printing, and I've got a little example here. What we call this is a closed cell foam structure. Looks quite natural. The reason why we're using this as part of that shell structure is that we only need to solidify certain parts, which means we have to bring less binder from Earth and it becomes much lighter. Now, that approach of designing something and then covering it with a protective dome, we also did for our Mars project. You can see it here, 3 domes, and you see the printers printing these dome structures.